Hi, my name is Ronald Luiten. Pleased that Marek calls me an old friend. I just know what the old pertains to, my age, or just that we've known each other for some time. I used to work for IBM Zurich Research, 35 years and a bit, and recently I retired to go and pursue other things, and I now have my own company called Data Motion Architecture and Services, GmbH. So today, perhaps you can show the first slide. We have an interesting session. We start with, I don't know exactly how to pronounce his name, Guarav Kaul. I don't know what his nationality is, but he is a senior architect at HPE. And okay, the slide should change. It doesn't for some reason. I click again. He's a senior architect consultant at HPE, where his expertise is on cloud and on edge. And there it is. And let's give the floor to him for an interesting presentation.
So thank you everyone for joining today's discussion on the topic that is around memory and interconnect interplay in today's AI and HPC systems. So my name is Gaurav Kaul, and Roland, you pronounced my name correct, so that's great. What I'll be talking about today will be how memory and interconnects are becoming central to large-scale exascale and AI deployments. And I have broken down this talk into several sort of trends that I see. And these trends are basically impacting system architecture. So my focus will be on those trends, but what we'll try to see is how these trends are shaping up system architecture and will shape, the next, let's say, 3 to 5 years of HPC and AI. And then we will go into, how these trends will, how that architecture will look like in the near to mid future. So I think most of you have probably seen this, so I'm not going to dwell on it. But this is a very interesting sort of phenomena in which both AI and HPC are getting more and more compute bound and compute hungry, whereas the main, let's say, or at least one of the main sources of compute performance that Moore's law provided us is slowing down, and I think now there's no debate on that. My apologies to my I'm ex-Intel, so my apologies to Intel colleagues that we always often debate around Moore's law, but I think one thing is quite clear, that Moore's law is almost kind of not stopped, but is definitely slowing down. There's no doubt about that. So, and this has come at a very bad time when we have a lot of requirements around compute, thanks to deep learning and thanks to exascale, that which has really grown from strength to strength. Um, in parallel to that is this whole analytics workloads that is moving around cloud to edge, which is really key for some of the deployments that we have around 5G and AI. We are seeing more and more compute being pushed to the edge as well, and this requires both compute architecture innovation as well as memory system performance innovation, because data movement from cloud to edge is definitely the limiting factor in cloud to edge deployments. So this is just one level of one kind of architecture, which we have worked with some of our customers in HP who are looking at doing edge analytics. For example, autonomous vehicles customers, who are looking to do this kind of edge analytics, but not only do they require performance at the core side, so core as in the cloud or the private cloud side, but also on the edge side. So how do we create this kind of architecture which kind of supports both these deployment models? So these are some of the technology trends that I will talk about, which we are already seeing, let's say, developed in different silos. But those silos have not been integrated yet, or are in the process of integration. That's going to take some, time that journey takes. But we are seeing this. So some of these trends are, some of which are well underway, is domain-specific acceleration with GPUs, TPUs, wafer scale engines, so on and so forth. There's also a push towards standard software infrastructure, mainly driven through containerization and orchestration, such as Kubernetes. We are also seeing a lot of innovation coming on the silicon photonics end, things like co-packaged optics, for example, from IR Labs, for example. So that's really key. One thing that's of interest to me is, and also to lot of the folks, I guess, on this presentation, is near data processing. How can we come up with algorithms and architecture which supports near data processing? So, going back to what I said, optimizing for data movement rather than compute performance. Hyperscale and cloud deployment is here, and we are seeing a lot more. When I say cloud, I don't mean public clouds, but cloud as an architecture. We see a lot of customers adopting the flexibility of the cloud, and that's why, for example, for some of our HPC workloads, customers are moving the entire supercomputer, such as Cray machines, to Azure infrastructure, just as an example. So this is definitely happening now. Disaggregation at rack level, thanks to presentation, or thanks to influx of storage class memory. This is something that is also just starting now, and we will probably see. And closely aligned with that is interconnects like Gen Z, like CXL, which will provide memory coherent fabric um, to these domain specific accelerators, and allow us that, how can we and disaggregate the compute from the memory, and create a, what I would say, a new form of server architecture, which currently we do not have. We already see some companies in this space, who are building up their, let's say, DPUs or smart NICs, which are, I would say, first generation of this kind of interconnect. But once CXL and Gen Z become more prevalent, this will lead to new kind of innovations here. So I will talk about these trends in a little bit more detail, starting from the next slide. Next slide, please. So I think, again, this is probably not new to any of you. We are seeing domain-specific accelerators for specifically for AI and machine learning. I think in some time we will also see these accelerators being used for HPC. There's already some work being done, for example, to use TPUs, for example, for physics simulations, which is interesting. So these accelerators, which have been created specific for deep learning and optimized for, single precision or even lower precisions, those probably are not directly suited for high performance computing. But what we see is that the incorporation of some of these, let's say, tensor processing units onto chip architecture, that is something that will that is something that, for an HPC like workload, could be beneficial. So for example, we could have matrix engine matrix multiplying um, uh, you know accelerators, or some accelerators specific to a particular workload like FFT, etc., which can be embedded into the chip architecture, and therefore, we get some kind of domain specific acceleration. That is something through chiplets that people are exploring. But we definitely see that in order to get more from Moore's law, in order to get better performance, now that Moore's law is sort of slowing down, domain specific accelerators are definitely the way to go. Um, you know, with regards to FPGAs, there have been some deployments where FPGAs are used for large scale machine learning, and that is definitely one avenue of specialization. And the extreme form of that specialization is through ASICs, which, for example, is being done in Google's case through the TPU. So I think DSAs are definitely here to stay. Of course, GPUs are being used predominantly for this, but we see that this will be a very wide sort of a design space, where, other specific accelerators, whether those are wafer scale or data flow based ones, each have their own strength for a specific workload, and they can be used based on that specific workload. The really the crux of the problem is, how do we orchestrate, workflows based on these different kind of domain specific accelerators. I think that is more of a software problem, but that we will see later. And this is something that hyperscalers are trying to handle as well, because they run mixed workloads in the cloud. It's not just HPC, and not just AI, but those are mixed workloads. And there's a very interesting trend here, And I think this is something that this new form of HPC that we call fluid HPC should be aware of. So this this methodology of disaggregating accelerators, the so-called compute plane, and the control plane, which is what basically drives this compute plane and basically orchestrates workloads across the compute plane. So this was first demonstrated by Microsoft in their, I think it was called Brain Alpha Wave or Brainwave architecture, which used FPGAs. So the difference here was that each FPGA has its own network interface card, and this provided a network connectivity between different FPGAs. So you could basically create a compute plane and map your deep learning network onto these collection of FPGAs, thereby creating that compute plane. This is something I think the cloud vendors have really innovated across based on the scale that they have. So this software-defined way of programming acceleration or accelerators is really unique to hyperscalers. And I think as we go towards exascale computing, so a lot of the large scale HPC will start looking like these hyperscale deployments. So how do we have this control plane versus data plane or compute plane, whatever you call it? How can this be architected in a more fluid way? I think that is a real big question in HPC right now. Next slide, please. Um, in parallel to that is this whole concept of near data computing, which we I think all understand intuitively is that it's the because we are bound on the movement of data. It is the movement of data that basically dissipates most energy. And if you look at both exascale and AI, they are essentially energy limited. So exascale, for example, we already are touching 30 megawatt of compute performance. Sorry, 30 megawatt of power requirement on a specific compute performance envelope. So this is essentially becoming a way of optimizing for energy, and near data computing allows us to do that. This has given rise to a new form of, I would say, not a new form, but it has spurred innovation in smart NICs, computational storage, and intelligent memory controllers. And the whole idea is that rather than just moving data around, can we actually process the data into these smart controllers, smart memory, or smart NICs? And basically, just like we do for GPUs and TPUs, can we offload computations to these devices? So they basically become a pair to the main CPU complex rather than just some dumb devices that funnel data around. This is really interesting development, and I think near data computing probably was sort of didn't have an architectural plugin that could sort of create a system architecture which kind of utilize near data computing end to end. But now with smart NIC, smart storage, and hopefully soon smart memory, thanks to CXL, this will probably, as a philosophy of creating computer architecture, will really come out through. So this is something again that will be very interesting to see in the next 2 to 3 years. Next slide, please. Another thing, and this is probably not really related to too much on the on what we are seeing in terms of memory and interconnect, but nevertheless is really important, is the innovation that is coming in packaging, and specifically in chiplets. Essentially, what a chiplet is that it allows us to take mixed piece of function, a logic, essentially a logic element, and integrate that at a chip level onto the larger CPU complex. And this is really interesting because it allows us to scale the number of cores and actually have diversity of the type of cores that we want to do. This is already very prevalent, I would say. For example, AMD's EPIC processors already now in their third generation have really progressed this, right? So what you have in EPIC is essentially a chiplet-based architecture in which the core, the CPU cores are actually, I believe, of 7 nanometer, for example, in the latest generation. But the other cores, whether they are I/O or memory, can be of different generations. They could be, 16 nanometer, for example, or 14 nanometer, whatever TSMC uses. So what this allows is that it allows chip vendors to not just innovate on the current, let's say, um, node technology, whether it's 7 nanometer or 5 nanometer or soon to be 3 nanometer, but also integrate older process technologies and thereby increase the yield of these and thereby increase the yield and lower the errors and keep the costs under control, which are really becoming very difficult given all the focus towards lower advanced process nodes. Chiplet help us do that, but more interestingly, they also help us create interesting kind of domain-specific architecture in which we can, rather than just package CPU cores, we can actually package domain-specific architectures into this. This is currently not there yet, I would say. Perhaps you can say some of the chiplet-based FPGAs can be considered like that. So, for example, what Xilinx does in Versal, but it's not mainstream yet. But this is something that I think will become mainstream pretty soon. From what is coming from Intel side, and already AMD already providing that. So chiplets is one way where we have a viable path to keep Moore's law alive. The next slide, please. Yeah, so an example of chiplet is really keeping this 2.5D interposer architecture. Which we already see. One thing I must say is what extra thing that chiplet has allowed us to do is provide this high bandwidth memory integration on top of on the chip on the chip package itself. And this high bandwidth memory has basically, this is what allows us to train these large neural networks um, with like GPT-3, for example, which has 7 billion parameters, and now some of the vendors are talking about trillion parameter models. This kind of scaling can only be achieved in a way that provides us the bandwidth to feed these compute engines. And the only there are several memory technologies, but the memory technology that is most predominant in these kinds of accelerators is HBM. So chiplet has already made a deep impact by integration of these HBM memory technologies onto the processor or onto the GPU package. This is very interesting because what it allows us, and what it's pointing to, is that we could have other similar, let's say, memory technologies, whether those are storage class memories, etc., possibly packaged into the same kind of thing. I think this is a bit far out, but this is something that will happen thanks to this 2.5D interposer technology that's happening. This is not necessarily chiplet, but also there. Um, Very similar, very closely aligned with this is the innovation in processor to memory interconnect and processor to processor interconnect. IBM already has been working quite a bit on this through OpenCAPI, but what we had seen is that there was no common industry standard which would allow us something like this. And CXL and C6 is probably the first step in this direction. Once we have this, this would be really something that will give us an idea that how we can integrate all these different technologies, whether those are chiplets, accelerators, memory, into this whole, and make it completely coherent. So I
Guarav,
think
I hate to
yeah,
interrupt you, but
yeah,
you're at the end of your presentation, so I don't know how much slides you
sure.
have left, and we should
Yes,
have a little bit of time for Q&A.
yes, I can. We can go to the summary slides because I think we have pretty much covered all the trends. And what I will do is I will sum up. Yes, summary as well. Just if we go to the summary slide, please. So, I talked a lot about some of these technologies and trends, but the idea is that, how can we bring these technologies together? So, what really is allowing us to provide, spur the innovation in these technologies is generally AI and exascale computing. And this requires us as architects and as software developers to, in my view, work closely across three main parts of the system. So one is near memory computing, another is disaggregated server architectures, and then domain specific accelerators. And there's a lot of work that's already happening in each of these three domains, but I think we need to work closely and bring all these three trends together so that we can have a cross stack kind of innovation, I guess not a completely new, but really system architecture which can leverage all these three things together. And this is what will drive performance in the coming years. And without the software stack, of course, we will not have it's it will be kind of not usable. So the work that is being done thanks to Kubernetes and this control plane, data plane separation that I talked about, containerization, I think how can we leverage that as a software stack to make this HPC more fluid. I think this is going to be very interesting development in the next 3 to 5 years. And with that, I will end this presentation. Thank you for your time.
Okay, thank you. Very interesting. In fact, the company that I founded is working on a domain-specific accelerator for weather and climate. And my question, I haven't found any questions from the audience, so I'll ask one question and move on to the next speaker. My question is, do you have any common requirements for all those domain-specific accelerators from a system software viewpoint?
Yes, Roland. So I would say, in terms of common requirements, I think what we are seeing is that, at a fundamental level, most of the requirements boil down around doing arithmetic, around matrix multipliers, or around these kinds of logic in a way that is much more powerful and much more customized specifically for that particular workload. So so to give you an example, we are working with a few vendors and startups, and this could be something we can discuss also, is how can we do, for example, lower precision arithmetic, or make a tensor core that that does various forms of matrix multiplies on lower precision, let's say using POSIT kind of arithmetic or something similar, but do it in a way that is more similar to how HPC workloads kind of expect it. So I think some work needs to be done in order to come up with a common criteria, a common set of workloads, and put that into a chiplet sort of, put that into a domain specific kind of thing. And this is where I would say OCP is doing some good work. Is that what they are doing is their OCP is Open Compute Platform, is that they have open domain specific architecture project, which is looking at creating a common infrastructure in which they can take different chiplets and bring them together in the same package. So in future, you could have, for example, matrix multiply units, you could have deep learning ones, you could have FFTs, and so on and so forth, uh, chiplets which are integrated into a control processor, and basically use that as a specific kind of thing. So I think we are going in that direction, but a lot of work needs to be done on the integration side of things.